theme of Jeff's career, he follows Keck Observatory and the use of Keck Observatory throughout. Jeff specializes in a lot of topics: damp light and alpha systems, high redshift galaxies. Interestingly, in the time domain astrophysics, he spent a lot of time trying to understand type 2 supernovae in the high redshift universe, trying to look at different things that go bump in the night. Now today in the time domain, I learned he's leading a project called Deeper, Wider, Faster, DWF, coordinating tens of telescopes across the southern hemisphere for following up fast radio bursts. And he's a professor now at Swinburne University of Technology. I probably hope I said that right, at the ARC.
You did.
And today, while Jeff wears many hats, he's coming to talk to us about Keck Observatory and a future instrument called the Keck Wide Field Imager.
Thank you, Shelley. Very good. Hello, everybody. Hope that people can hear me fine. Yeah, we're talking to you about an instrument for Keck in the future. So it's an instrument talk. Hopefully I make it interesting enough for everyone. There is some science in there. I'll tell you about what it can do. That top line there, the most powerful wide field optical imager on Earth or in space for the foreseeable future, is actually true. It's not just a big exaggeration. Okay, so that's important to know. So that's something that is kind of underlying the reason why this is being pursued. It's a partnership between Australian universities and institutions and US. And as you can see, there's a bunch of logos here. There's Swinburne, where I'm from, which has a factory of the future. It's a funny name, but whatever. And then there's a computing services where they do computing work that I'll be talking about. And then there's the ANU University in Macquarie, which has the Australian Astronomical Observatory. That's part of this program. Then there's the UC California system of observatories, Caltech with the COO and Keck itself. These are just logos for centers of excellence that are involved as well. So this is the science team and, the KBIT team and the science team. There's some overlap between the two, and there's just a lot of names here, so it just means a lot of people involved. But a lot of good people at UC, especially in other places, doing science for this project. But there are some key people at the top at Caltech, like Rich DeCaney, and there's Matt Radovon at UCO, and some other people that are the brains behind this design and this high throughput design that I'll be talking about. So this is a picture of Keck. I think everybody knows and loves it. It's a flagship of our university system. And this is where KWFI will go. It's this hexagonal prime focus region on Keck. So it's up the upper part of the instrument. And this is just a view of it from the inside, taken from inside. So imagine down over here is the prime mirror, right? So the light comes in and typically comes up to here, which has a secondary mirror, and then sends it back down to Cassegrain instruments or some other instruments that might be out on the platforms and Naismith and stuff like that. That's the usual operations that's been forever. But we're designing a camera to sit here and in place of that mirror, as I'll show you, and we can take imaging there. It allows us to take wide field images. It's a computer drawing of that page with the baffle here. And so the camera is all the colored parts here. It's just showing a nice computer image of it. This big red ring thing is I'll be calling it the module, and it's a just big metal thing that rolls it in and out. It's for installation and just rolls it in out. And as you'll see, Keck was designed to do this. So interestingly, this instrument had some long history. And as we started getting into the development of it and seeing all the wonderful potential, looked through old documents back in the 80s that were written about Keck's design, Keck Blue Book from '85, and they designed a wide field imager for Keck. It was actually designed from the start to have a wide field imager. It just never happened. So Jerry Nelson, Sandy Faber, and Terry Mast were behind that, and Harlan Epps did the design, and it was meant for this. So it's not something unusual. It's what Keck was built for. It wasn't built back then, I would guess, mainly because this is back in the day of photographic plates. CCDs were new and they were tiny, and to pile a giant field would be very expensive, things like that. So I think it was kind of shelved for a while. And then, of course, Keck did so well with deep spectroscopy and AO that it just kind of stayed in the background. Okay. So I'm going to introduce you to the instrument really fast, just so you get a sense of what it is. So when I give this rest of this talk, you'll know what I'm talking about. This is a cutaway slice of that instrument computer drawing I showed you before. It's a very, very simple instrument. It's low risk, just a simple design, but it's very powerful. And so this is the top end module I was telling you about. That red thing is the thing that rolls it in and out for installation. And one reason it has such high throughput is it has, here are the corrector lenses. It has only 4 lenses that does the correction on this wide field. Now that, if you don't know a lot about instrumentation, that's actually about half the number of lenses that are usually used in this case. And that allows for fewer surfaces, less glass, and higher throughput, let alone lower cost and lighter weight too. So that, and this includes adaptive atmospheric dispersion correction, which I can discuss with people if you're interested, but it's an active system, so there's no additional lenses involved here. This is the camera barrel that holds things together. Here is a thing called a hexapod, which is a piston-like system, which gives this whole thing like 6 degrees of motion, so it can correct for flexure and focus control, thermal control, things like that. This is a rotator, this blue thing. So everything to the right here actually rotates, because when you're imaging, a field on the sky, it'll go like this, and it's, as it goes across the sky, it changes its orientation with respect to where you're looking at. And Keck's an as telescope, right? It moves this way and this way, so you have to rotate that image to keep up with the field. This is a filter exchanger. I'll be talking about this in the talk. This system here, the gray here is it holds 8 filters at any given time. That's just an example of a filter. This is a shutter behind that. These things are large. That's like 2 meters in size. So you can imagine this is a pretty big instrument. And this is the detector, and it comes with like the cryostat and electronics and stuff. And that's it. I mean, it's a very simple, straightforward instrument. So that to show you the wide field nature of it, this is the computer drawing of its focal plane. It has these really large, has 12 6K by 6K CCDs. And this white circle is a degree across. So you can see it has a degree across field of view. Overlaid are these other instruments that Keck that can, image, quote unquote. I mean, most of our images in the infrared, just fine on axis. LRES is an off axis optical imager. This is DEMOS, which could, in principle, image, even though no one uses it for imaging, but that gives you a sense of the field of view of instruments on Keck, and this is much, much larger. Also, this design has CMOS detectors in the corners here, and these are principally for focus and guiding and things like that to keep the thing operating, but they can be used for science. So if you have any targets that you want to get very fast cadence images, like down to milliseconds, this is interesting for you, because when you take a very fast exposure, as you know, they're very shallow necessarily, because you've just exposed very quickly. But now with 10 meters of glass behind you, you actually can do some good science, because you can get some depth as well. All of this is based on the successful Transient Facility, which is at Palomar, and that's been operating for years. And so all of the R&D that went into this detector package, array, et cetera, is now just being modified for this. So that saves a lot of money and has heritage there. Thinking of the field of view and other telescopes, this tiny little red square is Hubble field of view. This is the Roman footprint. So the Roman Space Telescope that'll go up in like 4 years or so is infrared wide field imager, like 100 Hubbles they claim is the advertisement. That's its field of view. And this is LRES field of view down here, this blue. So if you wanted to say, this is it, the Hubble Roman is infrared. So if you wanted to say cover that with optical, you would use LRES, and you can see it would take many, many pointings and lots of time and expense, right, to cover just one pointing, let alone many Roman pointings. Euclid is going up next year, and it has this size footprint, so another infrared, wide field infrared space mission. And this is the field of view of KW5, so it's well suited for these types of fields of view. So you can get just in one shot, deep, very deep optical, and as you'll see later in the talk, that's crucial to the main aims of those missions. Okay. And lastly, I put some dashed lines here because there's a facility called Mauna Kea Spectroscopic Explorer that may be built from the CKHT telescope, and that is a 11.25 meter telescope that has a wide field, this wide field, the orange there, spectroscopic capability. So it's going to get very deep spectra over a wide area. So you can see already that it's going to need very densely, there's thousands of spectra, so you need like something that can get a very dense sampling of very faint sources, and KW5 can do that. And there's this instrument called Phobos that is planned for Keck, and that's still the views in the green there. And there's Subaru PFS, which is also about the size of that orange MSC footprint. So all these are instruments which I'll mention in just a minute anyway, but there are things coming that are suitable in field of view size. This is the instrument from the side. again, computer drawing, right? So the camera is all here. There's a deployable secondary mirror on the front, which I will discuss more in detail, but the front of the camera is at the teal end here, but that gold piece there is a mirror, and that mirror will be able to flip up, so you can use the camera up in the secondary, and then you can flip it back down and then use everything else on the telescope. And as I'll mention later, we're designing it such that you can process these images from KBIT within just a couple minutes. So in theory, you've got a telescope, take some images, and in a few minutes already have your sources, configure a spectrograph, flip it down, and then get spectra. So it'll be a nice new capability to be able to do everything really fast in the same night. And I'll talk more about this later. So why KBIT? Why would you build such an instrument, right? Even though it sounds cool and powerful. Well, before I say some stuff up there, I want to mention that if you look back about 100 years ago, there were like 1 meter class telescopes that were taking, plates of the sky, and you're finding objects, and you find sources in those images, and then they were sent to like the 4 meter or Palomar telescope to get spectroscopy, because you need a bigger telescope for the fainter spectroscopy. And then as the 8 meter and class telescopes in Keck came online, now the 4 meter class telescopes in Palomar were used to find those deep sources like Lyman break galaxies, for example. That spectra were then gathered by the bigger telescopes, right? 8 meter and 10 meter class telescopes. Well, now we're entering an era with JWST and then soon 30 meter telescopes. We now need 8 meter class, 10 meter class telescopes to be doing that job for those instruments, finding those faint sources, rare lenses, and things like that. But in general, the wide field imaging is just prevalent everywhere in astronomy. In most science cases, it's there somewhere, and others depend heavily on it. This also includes all wavelengths, like radio, high energy, particles, even gravitational wave detection require localization from an optical wide field imager. You need to find these things in their host galaxies. And these are the highest, if not the highest demand instruments on their respective telescopes, which is a testament to the fact that they're just needed. I mean, they're very important. So if we look at 5 years to say 10 years in the future, what do we have? Well, I mentioned these wide field spectrographs that will be our planned. So they're going to be needing this kind of imager to help them, their cases. There are also these other, mega facilities or billion-dollar facilities that are the square kilometer array. If you know about this, it's a radio facility coming online. There are some pathfinders already operating called ASCAT near KBIT, if you know about that. There's a Tranquil telescope array working in gamma ray detections, KM3net, which is also like a improved ice cube for particles. Those are all wide field or all sky telescopes. Then of course there's the 30 meter telescopes, CMT, GMT, and ELT, and James Webb Space Telescope. Those aren't wide field facilities, but they need they can get very faint spectra, and they have that capability. Then there's the gravitational wave detectors, right? There's LIGO, Virgo, Cagra that are online. And I'll discuss later that these have found gravitational wave events, and already they're finding sources farther and fainter than we can reach now. So we need something bigger, yet in the future, they're going to be more and more sensitive. So we're going to be in a worse position in the future. So the need becomes greater. And lastly, these space-based missions like Roman and Euclid, which are like, decadal review, #1 priorities, et cetera. They're infrared-based telescopes, and they also could use these, need this deep wide field optical.
What about the telescopes like
I'll mention in a minute, but LSST, is a survey of the sky telescope, and it'll probably make sense a bit on my next slide here, and if it doesn't, I'll push that. So what facilities exist, right? And so if you think of a large wide field instrument to do either a deep survey or to follow up things like gravitational waves, et cetera. So an instrument has to be like 40 meter class or larger in this case, I'm defining, and wide field meaning something that you actually tile the sky without having to do a gazillion pointings. And if you look at what's there, we have CFHD Megacam, which has 3.6 meter, 1 degree imager. There's the CTO dark energy camera and Super Hypers Prime Cam, and then soon the Rubin Observatory. And here are some comparative, primary mirror sizes there. But if the Monarch Explorer, Spectroscopic Explorer goes forward, Megacam and CFHD will be dismantled for this. And the lifetime of Megacam is unclear, so I'm just kind of knocking it off the list here right now. And I'm going to be done with these three. So these are going to be what we're going to look for, or these are existing or soon to be imagers for the foreseeable future for some decades. There's nothing else planned. So DECAM is on a 4 meter, it does a great job, but it has poor U-band sensitivity, which I'll mention later is important for a lot of science cases. And it's also a smaller instrument, so it goes shallower. Hypersur PrimeCam is a great instrument. However, it has no U-band at all, which is important. Its optics are shared with this prime focus spectrograph coming online. So even though it has a, some access now, that access is going to be less later. And there's actually talks that might be retired. I don't know, but it also has some other issues in the fact that to change the filters, it takes 30 minutes, which is a long time. If you're on Sky and you're sitting here for 30 minutes waiting for a filter to change. And if you're doing transients, for example, you don't have that time a lot of times. So it no longer becomes a transient or TOO follow-up facility. And there's some other aspects that are that matter compared to KBIT. And then there's the Rubin Observatory, which will do a fantastic survey of the southern sky. It's going to be great, but it's going to be doing that for 10 years. So during that time, you can't like propose Rubin to do your science. If you wanted to do a science project, you can't propose on it. You just have to wait for the data to come in and use that, which is good. But when it comes to target of opportunity, following up transients, there's discussions on will there be at all, but it sounds like it's going to be maybe 1 or 2% of the time, which is like 3 or 6 days a year that you're going to be able to follow up transients. That's going to be interesting, but it'll not be a major feature of that telescope. So with Keck and the wide field imager, not only is it on a 10-meter telescope and has much higher sensitivity than any of these, but it also has superb U-band sensitivity, which none of these have, and no other telescope in the world has this. And one comment is, since this has been known by the community, U-band science cases have just been coming out of the woodwork. Everybody needs it for so many science cases desperately. So it's a very important feature. It also will have this TOO, or its location at 20 degrees latitude makes it cover all of the northern and 2/3 of the southern sky, but it's also able to do this TOO capability or following up things quickly. When you think about that, following up objects quickly from, say, gravitational waves, for example, into the decades in the future, all you really have is DECAM. Because if KBIT is not built, you have a 4-meter telescope in the southern hemisphere to do all of it. And it's already 10 years old, so that's just giving you the landscape. Okay, so having KBIT is needed. I shamelessly stole this plot from Hilton Lewis's talk, who's the director of Keck. He shows this metric where you have like the median impact per paper versus its total impact, and the colors denote, high impact papers, et cetera. And it's basically saying that if you're the upper right of this plot, you're doing well. Okay, if you're up here, this is great, down there, not so great. And here's Keck's doing well. There are things like ALMA doing better. And ALMA, and there's some radio facilities on here. So I took the liberty to say, well, let's just get rid of the radio and look at optical infrared only, because we're talking about optical and makes it look better. So if you just look at optical infrared, then you have this plot, and Keck's doing fantastic, right? But of course, when 30 meters come online with JWST, they're going to be really high impact, and Keck will now no longer be the leader, right? And so you have to say, what can we do to help keep Keck going this way? And if you look at its competitors, 8-meter class telescopes, here's BLT, Super Gemini, so Keck's doing fantastic. But interestingly, here's CFHT and here's Blanco. These are 3.6 and 4-meter telescopes. That's interesting. They're way up here for these small telescopes. And why is that? They have wide field imagers doing crucial fundamental science. And I think that aspect added to Keck will help Keck move up in the future. At least that's the thought. All right. So this probably should say why Keck as opposed to why KBIT, but why would you want to put on Keck versus some other telescope? Next goes back to this design, as I was telling you. It's up in this prime focus cage of the telescope. And as I mentioned, Keck was designed to do this. So if you can imagine, this is a telescope pointing in the sky, but say you wanted to point it down to the horizon, it would look like this. And as you point it down, there's this horizon deck where you can just access it really easy. And so for the top end of the telescope and actually the underneath bottom Cassegrain, it's exactly identical. You just put instruments in and out. It's kind of designed in this modular way. And so that makes it really nice. Other telescopes, you have to take off the whole top end. It's a whole day, 2-day process. It's drama. So So if you look into this cage, you see there's stuff in there, and what happens is that module will roll out, and this is that module. It's like that red thing I was showing you in the computer. So you can imagine the camera goes in that, going in and out. All right, so another reason why Keck is that it's at over 4,100 meters or 14,000 feet, and because it has very, very high UV transmission, and other facilities don't have this, and even the 30-meter telescopes are at lower elevation, so look for UV transmission. So it's perhaps the world's best site for this, yet it's not exploited. No one's really doing this. So this is one thing too, to try to take advantage of that. And what that turns out is here's like a throughput plot of what KBIT will do. This is an old plot. I'll note that in a minute. But these are the 5 filters like UGRIZ, broadband filters, standard optical filters from 3,000 to angstroms to a micron. And this is the convolved throughput, these color regions. And if you look at the solid line, that's the atmosphere throughput, and that's that much through, and then it drops off at 3,000. That's just atmospheric Monarchia. The dashed line is the quantum efficiency of the CCDs that we chose for this plot. And we designed to make them very blue, so it has a very big blue throughput, which is missing in other instruments. And then a dotted line on the top is the optics, showing it's really good across the board. And what I'll say about this is, since this time, we've looked into thicker CCDs, which have a better red response without sacrificing the blue. So the new curves, which I wish I had here, but I don't, kind of go just like they do in the GR and I, but then UG and R, and then the I, it stays up pretty high, all the way out to about 9,000, 9,500, and starts dropping. So you can imagine this being flat farther, and that's most likely to be what is going to be the final decision on these chips. Now, if you look at this compared to Subaru is going to be these gray plots here, hashed lines. Now I'll clarify that this is a per second flux comparison. It's like if you pointed Subaru at some object and you pointed KBIT an object, this is what you would get. But Subaru has twice the field of view. So if you were tiling or doing a survey, you'd have to account for that. Subaru would be better because it's a bigger field of view. Okay. But for per pointing, this is just sensitivity arguments. You can see that it's, maybe 2 or 3 times more sensitive and will be 2 times more sensitive out to the red, and then infinitely more sensitive than you because Subaru doesn't have U-band throughput. And this would be the comparison, same comparison for Rubin, but also scale, because remember Rubin has a larger field of view. So yeah, but the point here is that the U-band at Rubin is pretty poor. It's designed more for red, and also stops at about 3,200 angstrom there. This will actually go down to maybe 2,900 angstroms, so down to 3,000. So here's a table of some of the depths you could get for time on sky. And again, I'll remind you that the I and Z will be deeper because of the thicker CCDs. But this shows you that you can get to 27 very fast, 28 in the very still also pretty quick. And then 29 is not out of the question for just a night observation. And of course, a dedicated survey maybe down to 30 if you need that for specific pointings. So that's kind of a new regime for depth. It's got very good pixel resolution, 0.145, so you get high resolution even in the best seeing. Our constraint is less than 15-second readout, and the current chips are about 10 seconds. So that's going to be very efficient on sky, because if you use Keck, some of the instruments take a while in the optical. They're a little slower in their readout. And I mentioned the filters, right? So it's going to have 5 broadband filters, but then there's you can put narrowbands in there, and actually room for 8 of any type per night. You just load what you want. And the filter exchange is about 10 seconds. And I'll show you that in a movie later, because we're actually building that instrument. So remember again, hyperspeed prime time is 30 minutes to change a filter. This is 10 seconds. And so you're going to be doing this during readout, just kind of seamlessly. You just expose. If you change filter, just keep going. There's no wait, okay? Which would be really nice for if you have needing multiple filters, different colors, or transient designs. And then of course, there's the deep U band, and it's got multiplexing for the 12, secondary, etc. As a last comparison, this is the LSSU survey from Rubin. So in the light blue or teal is Rubin, and purple is KBIT. And if you look at the depths at UGRIZ that aren't underlined, is 22.9 and 25, etc. That's how deep they'll get per visit when they're doing their survey. Now, after they do the whole sky many, many times, at the end of 10 years, so 10 years from now, 11 years from now or whatever, when they stack all of those together, how deep does that go? And the stack depth is underlined here. So they go pretty deep, right? 26 here, 27.5 and these other filters, so pretty deep on the sky. And remember, it's an all sky survey, not like KWFI. This is how long you would need KWFI to point at an individual pointing to reach that depth. So you can get the blue in just a very quick time, and then of course these last two will be shortened when we have a more sensitive. So it's very fast. And not that it would happen, but back in the envelope calculation could show you that you can actually kind of do a similar northern survey of the sky similar to LSAT in about the same amount of time with KWFI. This is now something like over a 20 million instrument versus a 700 whatever. But of course it has a Keck telescope behind it, right? It's cheating. Okay, so, but it's very powerful. So if you did need something in the north, it's capable. So now move on to science, and there is a lot. There are hundreds of science cases, and on here there's probably 20 or 15 or something. Things on here range from the solar system to local universe to high redshift randomization, transients, CGM, IGM, everything. And the things on here though, most of these can only be done with KWFI, which is interesting, or some of them can be done like so much better that it's order of magnitude. But then a lot of science cases are just better because it's a deep imager. And so I'll discuss a couple of these because time, right? So the first is going to be start from the high redshift. Let's look at randomization in the first stars. So I'll assume some underlying knowledge of universe, right? So neutral universe became reionized around redshift 6, et cetera. What caused that? And it's believed to be O and B stars, basically in star-forming galaxies and supernovae that emitted a photon shortward of 912 angstroms, so hard enough that they ionize the hydrogen. AGN are expected to have contributed, but the number of them seems to be dropping off at high redshift, so it's probably star-forming galaxies that dominated. But is that the case? And do we see them? How do they work? Why is that the case, et cetera? When you look at a high redshift galaxy, this is of course a low redshift galaxy, but if you just have a galaxy, you can imagine it's having some starburst and some gas and holes are formed that you can emit high energy radiation that's non-absorbed. It gets out and ionizes its region or a bubble around it. And that's what we're looking for. So this is a high redshift galaxy, redshift 4 spectrum. On top is the observed wavelengths, on the bottom is the rest frame. So this is in far ultraviolet rest frame. If you look at this spectrum here, the right here is the continuum from like O and B stars, and it comes along and you see this really bright emission line from Lyman alpha transition, and that continuum would continue, but it's absorbed by intervening hydrogen clouds in the line of sight, so it kind of suppressed in the line of the forest. But leeward of this 912 are photons that would ionize the universe. So if you see flux here, that's a smoking gun that this particular galaxy is emitting ionizing photons. Now, if you look at the 1D spectrum, you're like, yeah, I don't know, right? But if you look at the 2D, this is a zoom in of the 2D, and they argue that there's flux there, and this galaxy has got some flux. So some of these galaxies have been detected. This is a mildly lensed galaxy, so it also took lensing to help this prospect, because this flux is like 28th magnitude and fainter. It's very faint. So you need something to go very, very deep to find this. If I overlay the filters of KWFI, you can see them here, and you see that the Lyman limit continuum is right in the U-band filter. So you need a telescope that can image in the U-band very, very deep. Now, this is redshift 4, and if you go to closer, shorter redshifts, you can go down to redshift 3, but below that, this continuum is too blue to be seen through the atmosphere, right? The atmosphere only lets kind of 3,000 angstroms and higher. And if you start going redder, this now moves into the G-band. That sounds great. But the problem is once you get to redshift like 4.5 and 5, now the universe is opaque. There's too much neutral hydrogen out there. You can't see this flux no matter how big your telescope is. So from the ground, you can only do this work from about redshift 3 to 4.5, and that's it. And so to do that, you need the U-band. Find the flux, find the sources, get spectra. And because you can't do this during reionization, the only path forward is to find these galaxies, understand them at redshift, say 3 to 4.5, and then connect galaxies that have continuum escape to other properties they have, like nebula emission lines or ISM absorption line features, which are modeled to connect. Those can be observed at higher redshifts. So you do this connection thing. You first find them at lower redshift, and then you connect them to higher redshift. So that's the path forward. These are relatively rare on the sky because even though that emission comes out of these objects, it also has to make it all the way to Earth. And the chances of a transparent sight line all the way to Earth is not a lot. And so you need a wide field imager as well. If you do simulations of the early universe or just simulations in general, a lot of times you'll have simulation boxes of like 100 megaparsecs or 120 megaparsec simulations. And KWFI field of view at redshifts like 2 to 4 is this big. So basically 8 pointing per box, which is kind of nice. It's just a convenient measure. If we look at the first stars that go along with your ionization, too much on this plot here, but just know that there are supernovae detected from redshifts 2 to 5 right now. And there's there are core clap supernovae because they're UV luminous. And there's a class called superluminous supernovae, which are about 10 to 100 times brighter than normal supernovae. Those can actually be seen all the way to redshift 20. So like the very, very first stars. So, you know, Big Bang, stars form, the very first stars form, a couple million years later, they die, supernova, we see them. So it's like right at the very beginning. So they can be observed when you monitor the sky with imaging. If you look at their spectra, this is the optical in green and for ultraviolet in purple. These events are classified in their optical because they're studied locally. And they're pretty much just black bodies with some features, but not a lot going on there. But for ultraviolet, it has all the activity, all the transitions, all the things to help you understand the extreme explosion mechanisms and what their nature is. And also just understand their behavior. So the important thing is to study these guys, these events from redshifts like 2 to 7 with things like KBIT and spectra from JVST to understand this for ultraviolet, their light curve behavior, how they evolve, and also their spectra. Because when you start looking for these objects from redshifts beyond 7 out to 20, all you see is they're for ultraviolet. You have no optical. It's redshifted too far. Even if you use JWST mid-IR, it's still UV. So all these high ones, you'll only see the ultraviolet. So you really have to understand them and classify them and understand their properties in UV. Yes.
So I mean, at least from what I know, for cloud supernovae, the low redshift ones have they're very bright in UV for a short time.
Yes.
And so it gets some fine information on the UV pulse from.
Absolutely. So sometimes there may be only a few days in duration. Superluminous are longer. But these high redshifts, you've got time dilation, so now you've got.
That's what I'm thinking.
Exactly.
So, yeah.
Now you're less blurry. That's right. So it helps out a lot. Yeah, especially if you're at redshift 15 and you got to wait. I mean, for the whole event, you have to wait many, many years for it to evolve. Yep.
Sorry, quick question. Which space telescope is doing the UV imaging? Like, is the main one?
So for this would be KWFI would be the UV imaging is the argument here because you've got to go down to like 28 magnitudes kind of thing. You could use Roman when it comes online to do the infrared to do higher redshift once you've understand the UV, because then you'll see it at like say redshifts 13 or something. Yeah. Yep. Good. So quick summary, Lyman continuum galaxies are finding this escape. KWFI will find them, map them, what ionizing regions in this, or the regions of the universe that's being ionized in this range here, which is redshift 3 to 4.5. And then there's a square kilometer array, which didn't show up. Oh, sorry. I'll back it up. Oh, sorry. So it'll map in this range and then we'll connect it to properties, as I mentioned, that you can then observe higher so that you can understand ionizing sources through ionization. And then SKA is a radio telescope that's going to map the neutral hydrogen in this region. So now you have like neutral hydrogen maps and ionization maps. How nice is that, right? They work really well together. And when it comes to the supernovae, KWFI will study them in this range here from like 2 to 7 and find them and understand their for ultraviolet, trigger things like JWST to get spectra, to then understand their for ultraviolet to take it also all the way back to the beginning. So this is the idea. Next, I'll mention gravitational waves because this is a very important science case for this instrument. Gravitational wave occurs when you have like 2 neutron stars merge, neutron star black hole or black hole. And if a neutron star is involved in that, then you get this kilonova explosion, which you can see in all wavelengths, which is a great thing. And kilonova are very important and high utility. They can, heaviest elements are produced there. They can be used to measure the expansion rate of the universe. They can understand the equation of the state of really dense matter, et cetera. So they have a lot of utility, but we have one. Okay, there's only one known, one confirmed. It's not a big number, kind of need more. And the problem has been that firstly, the detectors to date don't have great localization. They'll say, okay, it's in this 100 square degrees or 1,000 square degrees. Good luck, go look for it. And then you try to tile it with an imager, and you've got to do in a couple filters several times to look for evolution. And you're racing around the sky trying to do that. So they're necessarily shallow images, because you only have like hours to maybe a day or two to find this before it fades away. And is it even up in the sky? Maybe it's close to the sun. There's all kinds of drama, right? And so that's been a challenging thing. But in 2027 and beyond, there'll be 5 detectors operating with increased sensitivity, such that their localization range is expected to be about 9 to 30 square degrees. And now we're looking at something that can be tiled pretty easily with something that has a 1 degree diameter. You can just go through that and do that. So the localization part of it will be mostly solved. Then it comes down to, what do we have to detect them from now into decades in the future? And all we have really is DECAM, this 4-meter telescope I mentioned. Ruben will be able to do some. Okay, and their cadence to their survey is not good for Kilinovi. It'll only see 1 data point and maybe, right? So this is what we have for the future. So you're missing all of the northern hemisphere, or most of the northern hemisphere, and you have a 4-meter sensitivity. With KBIT, you can now get this big area and deeper. So you get more than 90% of what'll be missed by those telescopes. And what I mean by that is seen in this volume diagram. So not only are you going to more sensitive telescopes, you're actually probing larger volumes. So if you have a 1-meter class telescope looking for an event that looks like the one that we saw, you can go out to about 200 megaparsecs. You have this volume around center on Earth. If you use DECAM, which is a bigger telescope, that's going to be our one that we go to. You can see pretty far out, 450 megaparsecs. With KBIT, you go up to 1200, and you can see the volume is gigantic, right? So you're going to find these things, and already they're detecting events fainter than we can see and farther than we can see already. 04 is going to start in March or so, and we're going to find more farther, and many will be missed because we just don't have the sensitivity now. In the future, it's only going to get worse. So this is the idea, is to have this be a capability. The last bits I'll just kind of go pretty quickly through. There are very high energy sources that produce gamma rays, and even particle sources, which the detectors detect, but they don't have the best localization. They have a localization, but you'll need an optical imager to actually find the source and the host galaxy, et cetera, to figure out what those are. Also, there's fast radio bursts, which you may know about. These are millisecond bursts in the radio that you can see halfway across the universe. So that's pretty cool. And you can use those to measure the ionized baryon content between us and them, but we don't know what they are. So it'd be really good to find out what they are. There is a magnetar in the galaxy that has burst and produced radio bursts. And so it's believed to be like an FRB. Those bursts are weaker than the ones we see extragalactic, but okay, so maybe FRBs are magnetars, it'd be good to know. But also there's evidence that there are multiple types of FRBs, just like there were multiple types of GRBs. So really good to get counterpart detections like they did for GRBs. And so going after them in the optical and getting spectra will solve that problem. So transients, I won't go through this, I'll just say the top batch up here of bullet points are cases where you would actually trigger the telescope and move the telescope and get some data and find these things while they're bursting and interesting. But the rest do not require that. It's just classical scheduling on a telescope. This middle section here, you can do a whole bunch of kilonova and high redshift supernova searches, et cetera, just scheduling classically, along with coordinating with radio and high energy telescopes, which also can be classically scheduled. There's large scale structure work, which over hundreds to thousands of megaparsecs of galaxy structuring, et cetera. Again, I won't go too much detail, but I will say that broadband imaging can actually do a remarkable amount of work here. So these are Liner-Break galaxies on the left here. These are spectra of Liner-Break galaxies, so for ultraviolet spectra, kind of what you saw before. There's like a continuum, a Lyman-Alpha emission feature, et cetera. And with just 3 broadband filter imaging of the sky, you can pick these out at specific redshifts like 2, 3, and 4 with like 95% efficiency. So that's already cool. You can already find these galaxies really easy. But if you plot them on a CMD, just a simple color magnitude diagram with these broadband filters, and you overlay the ones that have had spectroscopy, the squares are ones that have Lyman-Alpha absorption, and the blue are Lyman-Alpha emission. You probably can see there's like a blue emission and a red absorption here. And just from broadband imaging, you can carve out regions of space that are pure of emitters or absorbers. And so you say, oh, that's pretty cool, kind of novel. We can find out a spectroscopic feature with just broadband imaging. However, all of these other features are linked to that and they have relationships that have been found. So by just finding them, you'll know their morphology, their actual internal kinematics, ISM line strengths, their large scale environment, et cetera. All this information can be done from broadband imaging on massive scales. So I think that's pretty cool. Hopefully that gets, this is just showing that. I'll skip these two because they're just showing that they cluster in big areas on the sky and they cluster differently. You can also use narrow bands with KBIT to image emission of things like Lyman alpha, O6, and magnesium 2, et cetera. These are typically things you would see in absorption line spectra. But if you see these gases in the CGM and the IGM, you actually map them in emission. You can see where that gas is. So that's a very powerful tool because of the high sensitivity. You can also just see very faint diffuse things, right? Ultra diffuse galaxies, low surface brightness features on normal galaxies and how they interconnect with interactions. If you look at supernovae, you can study the remnants. You can look at supernova light echoes, right? If supernova goes off and that light goes out and hits some gas way out to the side and then comes to you. So you see that event actually happening, even though it happened like 1,000 years ago or something, but you need wide field imaging to do that, right? So these are powerful, deep wide field imaging. And lastly, I'll just say that this wide field plot I showed you before, these are the space missions I mentioned that are infrared space missions, Roman and Euclid. So they operate in this this wavelength range down here. And their main surveys are really only going to operate down to about 7,000 angstroms or so. And they're doing things like baryon acoustic oscillations, dark matter and dark energy with supernovae and things. But to do this well, because especially they're going down to like magnitudes 28 and 29 in these surveys, you have to have good photometric redshifts. So to have good photometric redshifts of your objects, you really need the optical here because that tells you the Balmer break and gives you actual photometric redshifts. I mean, it's really hard to do otherwise. And what's going to map out wide areas down to 29 magnitude? Not much out there, right? And so KWFI is going to take that range there and do that work for you. All right, so I'll just end with just giving you some summary of where the instrument is to date and how things are going. So I mentioned it was a partnership. So the US part of it at Caltech, they're designing and developing the detector based on this wiki Transient Facility, like I mentioned. At UCO, Santa Cruz and Berkeley, they're going to be working on the optomechanical and assembly and overall integration, including the camera barrel, et cetera. In Australia, the optical design was made and we're working on the lensing and optics there. Swinburne, they're building the filter exchange mechanism as we speak, and I'll show you a short movie on that. And they also are designing all of the instrument control software, the data reduction pipeline, because we want to have a very good data reduction pipeline working at the time of the instrument so that it makes your life easy, right? You just take an image and here's your data. So there'll be that. Here is that filter exchange mechanism movie. So this is so there's 4 layers like this. So they hold 2 filters each, and this is like the hole where the light comes through. If you can picture that on the telescope, this is 2 meters across, so it's big. But if it's operating, the filters just move in pneumatically that fast. And so you could be observing right now in some filter and you say, okay, I need to change filters, get readout time, and then that goes out and the next one comes in. This is just a weight to account for the filter weight on there. They move in and out really quick. So it's a really nice capability that's not offered on Supernovae, for example. Okay, and we're going to be testing that up at the summit in a month or two, and we're going to just take it through all the permutations. And at elevation, pneumatics can be weird, so we make sure everything works really well millions of times. And we're also working on this deployable secondary mirror, and that's this flip-up mirror thing that I was mentioning before. So this is, even though this is another complication, nicely though, it's just a one-direction motion. It's not a complicated thing like this tertiary mirror that's on there. It's just a. And this mirror is shown as a hexagon here because you really only need a hexagon because the primary mirror of Keck is hexagonal shaped. And also you need something that needs to be 1.4 meters in size. Interestingly, the TMT segments are 1.4 meters in size. So if we want to find a 1.4 meter mirror, I know where to find one, right? So all you do is just get one of those, reconfigure the shape, and then there you go. So that's one option. Also, there's a adaptive secondary mirror being thought about or developed to provide some ground layer adaptive optics. That also is a similar kind of design and actually would be better for us because it's lighter and works space-wise. It's just complicated in itself, so we'll see how that turns out. So yeah, remember, if it's up like this, then you're imaging, it's lights coming from the primary, and when it pops down, you can then get spectra, et cetera. And it can be on any instrument that's hot, so you can get a spectrum, infrared, optical, whatever. Lastly, if you are going to put a mirror in there and have that up there, you can just leave the camera up there permanently, more or less, just pull it out to maintenance or something. But if you do that, you got to worry about the laser launch package, because there's lasers, right, adaptive optics. And currently, that package is right here, attached to the module. And so we've developed or looked into it and said if it's attached to the cage instead, which is actually arguably more stable, that would work. And so this is going to be our design where it's out here, and that's the whole picture of the instrument. That's just it being pushed in and out. Anyway, so it just rolls in, and this can flip out of the way to enable access. So here's a short movie of a 3D printed version of KBIT in its cage. This 3D model was made at Swinburne. You can see its size here with this person. It's 1/4 scale, because actually that first lens is over a meter. It's a big lens. But this is a 3D printed model of it. It also is working model, so it actually shows that it rolls in and out, as it should. Remember that whole back end turns on the sky when you're imaging. So the back end will turn. If you take off the detector part of it, you can actually look in, and you see the filter exchangers here in clear, and they move in and out like you saw in that movie to give you a sense of how that operates. And then the next image is just looking through the back, and then you'll see it through the front. And so it's really cool to have this, because if you're trying to think of some design things, you're checking space and stuff like that, and just checking it overall physically, it's just cool to have too, right? A nice big model. Plus, if you got donors, you can say, "Oh, look, here's a really." Okay. So I mean, it's a nice thing to have. So that's nice. And I'll just end with the funding, which is this is the second to last slide. So far, it's been very strongly supported by Keck and the whole community. It's a nice, I mean, it seems to fit really well with the one likely future of the Keck Observatory in its decade from now. It's been funded through a feasibility study, a workshop, this conceptual design, even a proposal readiness review, and now we're applying for federal grants. And one was applied for in Australia, because again, it's a partnership, so partly funded by Australia, partly US. We'll hear about that in December, and then we'll be applying for NSF grants, et cetera, in this round. So that's pretty much it. Here's the timeline for when it actually started earlier than this, but in 2019 it was started in earnest, and that's when the design and funding was going. Right now we're in the major funding development part, and that everything went perfectly, and all the funding came in. Then we would start construction early next year, and then by 2027 we would have first light. Yeah, let's hope, right? And so just leave you with the fact that it can do science that cannot be done anywhere else on any other telescope, not even 30 meter. There are cases that it can do exclusively. So that keeps Keck at the top. It goes all the way down to 3,000 angstroms and maybe even bluer. It enables also new science by having this, flip in, flip out multiplexing mode, et cetera. And it's going to be very important for upcoming space missions. Thank you very much.
Questions for Jeff? Chris?
Hey Jeff, that was a wonderful presentation. I noticed that Sloan isn't on that one slide with all the things.
Sorry.
And Adam, for your information, York has 8,000 plus citations, so that's a paper a night, which is pretty decent. I'm curious, I feel like there's motivation somewhere
I think you're right.
for a survey or something like this, but I would love to propose it someday, so we'll keep that in mind. But my question is, when you do commissioning, I'm assuming there's some engineering fields that are picked out. I'm curious how those fields are picked and if that data becomes public.
That's a little ahead of the game right now. I do know there's gonna be a lot of testing on force calibrations and internal reflections. Also, we want to keep it lowest surface brightness, et cetera. But those fields are not chosen, and I don't see why they wouldn't be available right away. That's why. Probably Euclid and Roman deep fields is where you would go, because that's going to eventually be probably the only survey that I can think of that would be planned for this. Euclid has these 4 10 degree and one's 20 square degree details they find in Euclid, sorry, in Romans, thinking of the same kind of thing. And so because those are very deep and they're not that large in the context of the field of view, we would do very deep on those as a survey firstly, and then it would be more for just individual science use. Yeah.
All data becomes 18, after 18 months becomes public, unless otherwise waived.
Correct.
Yeah, George.
Two questions, Billy. So, first, I was very interested to see your slide on depth.
Yeah.
Which was impressive, right? You blow everything else out of the water. You also blow out of the water the reach of, the laser interferometer, ground-based laser interferometer gravitational waves. So for binary neutron star mergers, you're not going to get much beyond 200 or 250 megaparsecs, something like that.
That's orientation average. You actually find them about the 400-ish or so, but that's now. That's now. If you go into like
okay, but
cosmic.
here's my question.
Okay.
So that's for the ground-based laser interferometers.
Yep.
You have more reach in distance in the electromagnetic bands.
Yep.
And by the way, electromagnetism is somewhat stronger than gravitation. So you could actually invert this, and you could survey, look for something going bump in the night. And then, cue that up for the gravitational wave people to look at. My guess is the ground-based interferometers won't do anything, but the next generation space-based interferometers, there's an interesting thing because they'll see things at very high redshift.
Absolutely.
They should.
No, and you hit it in the nail on the head, because we've actually have some programs now looking for electromagnetic signature probability when gravitational wave detectors are off and beyond the horizon. So we've tried to do as far as we can. So you're right on. And KBIT will be able to go out to pretty high redshift, like redshift 1 or so. So now you have actually redshift evolution. But there'll be signatures that you have to recognize because they'll be on the gravitational detectors unless these newer ones get them. Exactly. Really good.
Yeah, my second question had to do with whether you can duplicate what hypersupreme cam does in micro lensing, for example, with M31. But we can get into that later.
Well, probably, depending on what mass scales you're thinking, it could be better because you got this fast readout. So if you want something that's in like minutes, you got a better sampling and you're deeper. So that is, yeah, exactly.
I think we may have some questions online.
Yeah, Allison wanted to know, at depths of 29th magnitude combined with ground-based seeing, are there going to be confusion issues?
Yeah, there are images that are down at 28 right now. So you just extrapolate that by magnitude. It's not going to be that bad, but it does start becoming, because it's ground-based seeing. That's right. So you do have to keep that in mind. Now, when you're in the bluer bands, it's usually less dense. And so the UGR is probably not too bad when you're in it's a good question, but it's just what you have to keep in mind when you image. Yep.
Karen?
You mentioned at one point narrow bands, and I was curious what was the plan there.
Yes, so the narrow bands, these are big filters, so not cheap. And so if you have some great science case, the ideas of some project funds it and they do that for their science case. But what's good about this is that we're working with Hypersupreme Cam right now, because they're also interested in this for the reasons you can imagine. And they have a set of narrow bands, like 12 right now. And if you look online, you can see what those are. And they're happy to share those across the mountain. So get some more extra use out of them. So if you had science that used their option line or HF or just whatever narrowband they have, that would just be accessible, because our filters are clear throughput is like 570 nanometers and there's like 580. So we decided to make ours 580 just so we can interchange and have that as a possibility, because it would save a lot of money in narrowband.
Jake?
Yeah, that's a good, so mass constraints on the secondary. So the secondary, initially when we're looking, a lot of things are still written in paper and 2D maps and stuff. So we're doing a lot of work there. It says 2T, so 2 tons. There's no scientific, like how accurate is that, right? And so after looking into it, it actually is more than that, especially since the whole top end is under kind of some pressure. It's like under this pressure situation. So right now we're at about 2.5 tons with everything. That includes this deployable. But this module I was mentioning, that red module that rolls in and out, that thing is 700 kilograms of just dead weight. You roll it in there and it just sits there and goes around in the sky. So we're designing it to just roll it in, mount it with a bracket, a truss system, roll that thing out and leave it out. So now we save that weight. So we're currently within the mass budget fine and space constraints. So everything is looking great, but we'll take a lot more development because Keck is old and things aren't always what you think, and you want to check everything actually. Yeah, exactly.
Are you looking at Keck 1 or Keck 2?
It can go on either. And the idea back in the day when we first started was, oh, you just roll it in at what you want, right? And there are actually people that wanted it for like, early twilight, or morning. But talking with the schedulers, it sounds like Keck 1 would be better because currently there's more dark instruments on Keck 2 according to scheduling. But Keck 1 also has the tertiary, so you might have a little more complications. I don't know if that's good or bad. So unclear at this point. And the laser was going to drive that decision, but in 5 years it might be later. So I don't know. I can't say, but Keck, I would prefer Keck 2 because Keck 1 has some bearing issues from the earthquake, I think. It
There's
has that sticky-
infrastructure there.
Yeah, exactly.
Very good.
But if it's not displacing another instrument, you just build two of them.
Good.
Why build one?
First rule of
Build two.
government funding. That's
You
right.
need a prototype to test with.
That's right.
It turns out it works.
That's right.
All right, with that comment, that's a good place to end. Let's
Okay,
thank Jeff
thank you.
for a really nice talk. Graduate students to stick around with Jeff for more
I think
questions.
he has to go.
No, I stuck with earlier. I got to catch a flight.
Sorry, never mind.
Sorry.
Jeff is leaving.
Yeah. But
Thanks for
thank you
visiting us.
anyway.
Coming back home for alma mater.
Yes, no problem. It's been great being here. Yeah.